Hello, my name is Mason Cipollini, joined by my lab partners Colin and Leif. This is Lab 4 for OPTI 471B.
To begin this experiment, we had to construct a beam expander. As the principles governing how a beam expander works were covered in the last video, we will omit those details here. Our beam expander setup consists of an objective lens, a pinhole, and a collimating lens. In this experiment, we demonstrate how a wedged shear plate can be used to measure the radius of curvature and focal length of several mirrors and lenses. The plate has a large 2-inch or 50.8mm diameter entrance aperture, while our input beam waist is just 394 microns. To maximize sensitivity and ensure accurate readings, our aim is to expand the beam as much as possible. The shear plate itself is placed after the beam expander. With the supplies we had on hand, we were able to construct a beam expander with a beam expansion ratio of 55.56, the largest ratio we could achieve with our materials. We used a 9mm objective and a 500mm collimating lens. This expanded our beam to roughly 42.8mm in diameter, filling roughly 80% of the wedged shear plate clear aperture. Next, we determined the optimal pinhole diameter by ensuring that at least 99% of the laser power at the objective focus would pass through. The governing equation is shown in the orange box. Our calculation gave a minimum diameter of 14.45 microns, so we used the closest available option, a 20 micron pinhole.
To assemble the beam expander, we first aligned the laser, microscope objective, spatial filter, and lens as detailed in the last lab. XY translations and the tip tilts of the laser align with the pinhole at near and far views. XYZ translations and tip tilts of the lens align with its retroreflections. XY translations of the spatial filter stage align the microscope to full intensity, and the fine XY translations of the spatial filter along with the Z translation of the objective upon the stage align the filter. Once the components are all individually aligned, we assemble the full beam expander, which consists of a 10x microscope objective, 50 micron diameter spatial filter, and a 500mm focal length lens. The assembly then leads the resulting beam into a 50.8mm diameter wedge shear plate, as the plate's interferometric geometry allows us to verify the collimation of our assembly. Our shear plate works by the wedge intaking the wavefronts of the ideally collimated beam and reflecting them onto the viewing surface where they will overlap. Within this overlap, fringes will be visible, which visualizes the beam's collimation. Contrary to the literature, we saw in our experiments that when the lens was inside the focus and the wavefronts converged, the fringes leaned to the right. Likewise, when the lens was outside the focus and the wavefronts diverged, fringes leaned to the left. Only when the fringes were horizontal will we be certain that the beam is collimated.
For each measurement made using the shear plate, an image was taken and values were extracted using a pixel measuring tool. Shown is the low-power mirror in one of its positions, with the shear distance, fringe spacing, fringe angle, and window diameter marked on the image. For the actual fringe spacing measurements, the distance across several fringes was measured and then divided by the number of fringes to obtain a more accurate number. Also shown is the equation to convert from pixels to millimeters by using the known diameter of the viewing window. For the low-power mirror and lens configurations, these are the equations used to calculate the radius of the wavefront, the focal length, and the error propagation. The radius takes the shear distance s, fringe spacing d, wavelength, and fringe angle alpha. For the focal length calculation, L is the distance from the mirror or lens to the shear plate, with plus for a positive power and minus for a negative power. For the error propagation, the partial derivatives were taken and combined using the standard method for independent variables. To measure the low-power mirror, once the beam was seen collimated in the shear plate, the plate was rotated 180 degrees and the mirror was placed after so that it could reflect back into the shear plate and produce fringes. Seen in the diagram is the setup. Measurements were taken at two locations along the rail to compare. Since alpha is positive, the wavefront is converging, meaning the mirror must be concave. At the first location, 590mm from the shear plate, a focal length of 100.1 meters was found, corresponding to a mirror surface curvature of 200.2 meters. At the second location, 110mm from the shear plate, a focal length of 104.4 meters was found, with a surface radius of 208.8 meters. Both had an uncertainty of roughly 12 meters based on a fringe resolution of 0.5mm and an angle resolution of 1 degree. To measure the low-power lens, the shear plate was rotated back to its original position, and the lens was inserted into the beam path. We measured a focal length of 88.4 meters, with an uncertainty of 12.3 meters. Again, a positive alpha was observed, corresponding to a positive lens.
In our final experiment, we determined the focal length of a high-power mirror. First, we rotate the wedge shear plate 180 degrees so that the entrance aperture is faced away from the beam expander. Next, a reference lens is placed after the wedged shear plate and creates a tight focus. That focus is then reflected and re-imaged by the test mirror. In the first step, we position the mirror at the reference lens focus until a cat's eye reflection sends the beam back through the lens, recollimating the output. The beam then passes through the shear plate. We adjust the mirror position until straight fringes appear on the wedge shear plate screen. This defines location 1. Next, we move the mirror farther away until it re-images the reference lens focus onto itself. This forms a 2F2F imaging system with a high-power mirror and defines location 2. In this configuration, the rays re-enter the reference lens so that the output beam is collimated. We verify collimation by making fine mirror adjustments until straight fringes appear on the wedge shear plate viewing screen. Since this occurs when the mirror is displaced by 2 focal lengths and the radius of curvature is twice the focal length, this method allows us to accurately measure both values by measuring the travel of the test mirror along the rail. These images show the viewing screen of wedge shear plate at positions 1 and 2. The effects of spherical aberration are clearly visible, making the point of best collimation difficult to judge. In both cases, the beam appeared collimated over a window of about 500 microns. Using the 2-position measurement, we estimate the uncertainty as plus minus 500 microns for radius of curvature and plus minus 250 microns for focal length.